Hello, I am Taylor Brown, and I'm working on exercise 1 of lab 4, where we are just working with an LM324, and we're looking at the slew rate of it. So we're basically walked through how to construct the circuit in these steps right here. So I've created that circuit here, and I'm using this portion of the LM324. So I'm only using this quarter, but I'm supplying a DC voltage of 15 volts to our VCC, and then the other side is connected to ground. I'm using a universal ground rail right here to the right. And then I have my resistors in place, and I'm using this function generator to generate a 0 to 5 volt square wave with a frequency of about 100 hertz. So I'm doing that, and then I'm using my oscilloscope, using 2 different channels on my oscilloscope to measure the input versus the output. And I've also done the simulation here. So as we can see, okay, the blue line is the input. So it's like a perfect square wave. It just goes up to 5 and goes that way, and I've zoomed in quite a bit, or changed the scale to 20 microseconds per division. And then the output, we can see, does the delta V does go higher. It goes to about 10 volts instead of the input of being 5. So here I have about the same thing. The yellow channel 1 is the input. It's just a square wave from 0 to 5. And then the blue channel 2 is the output. And as we can see, there is a slight delay from when it goes to 0 to the 10 volts for the delta V. And so that's what we're calculating for. That's the slew rate. So as we can see, I've just used my cursors to measure the time that it takes to fully turn on. And we can see here that it's 22 microseconds. And then I also... So I measured the simulation slew rate to be about 0.388 volts per microsecond, and I just used the oscilloscope function here and then read in these values. And then this is my in-lab calculation for the slew rate. So in our simulation it was 0.388, and in our in-person in-lab it was 0.44727. So they are pretty close. And our circuit does behave as simulated. So.
Hello, my name is Braden Black, and this is exercise 2. And so for exercise 2, the first part, we were asked to create a variable operational amplifier. And so our design, based on the 1 kilo ohm resistor value given, we designed our op amp to range from 3 kilo ohms to 39 kilo ohms, which in result gives us a gain from 4 to 40. And we can see that from the voltage values. Voltage in being 200 millivolts peak to peak, and then our outputs being around times 4 and around times 40. And so here's our circuit. And so we have our VCC hooked up with our 1 kilo ohm resistor going into the non-inverting terminal. And then we have our potentiometer set to 39 kilo ohms, which should be our max. And so after inserting our potentiometer back into the circuit and hooking up our oscilloscope, setting our VCC to 12, and our function generator to these values, we can see our different gains as the yellow is our input and our blue is our output. And you can see that the voltage peak to peak of the yellow, here our input, is around 200 millivolts, while we get a voltage peak to peak of 8.4 volts for our output. And this matches our simulation results decently well. Our error most likely being due to our potentiometer not being exact. And after now adjusting our potentiometer to be approximately 3K, we can now get the minimum gain of our circuit. And after inserting our potentiometer back into the circuit, we can find that our gain is approximately 4, with our input again still being around 200 millivolts, and then our peak to peak of the output being around 896 millivolts, which is again a little higher as well. Also most likely due to the potentiometer being rather sensitive, as it can range from 0 to 50 kiloohms. And so, as it is a large range, any tiny movement can change the output greatly. Alright, and so for the second part of exercise 2, we are tasked with creating an integrator. And so, as we can see here, we designed the circuit around the tau. And so we found our tau and solved for, we chose a resistor value of 5 kiloohms and then solved for our capacitor. Ended up being 200 nanofarads. And in our real circuit, we have a 330 or 3.3 kiloohm resistor in series with a 1.8 kiloohm resistor to approximate the 5 kiloohm resistor, and then we have a 150 nanofarad capacitor in parallel with a 47 nanofarad capacitor to add their values to approximate 200 nanofarads. And so in our waveforms here, we can see that it matches our multisim in creating a triangle wave from the square wave. In continuing exercise part 2, we're asked to change the duty cycle. And in our multisim, we can see as we reduce our duty cycle to, say 30%, our triangle output wave changes to kind of slope more towards the top. And whenever we increase our duty cycle to say 70% here, we can see that whenever the triangle wave decreases, it kind of slopes down. And as seen here, we have set up our circuit again, and with the same settings and at 50%, we can still observe our same waveform, this time zoomed in a little bit more. And as we change our duty cycle to say 30%, we can see it messes up the waveform quite a bit. However, if we pause for a second, we can kind of observe this sloping down that we can see. We can see particularly here in these instances that the waveform slopes up, matching our results from the multisim here. That sloping there. And then as we change the duty cycle to say 70%, as in our multisim, and then hit run, we can view again this distortion and this weird sloping as changing the duty cycle changes the period, and thus changing tau, and thus not matching our RC circuit that we designed correctly, and thus not producing the correct integrator.
Carter Hurst, 113-605-311. Here are the values that I've gotten for the VPP with the frequencies I've chosen. My circuit is on this half. This wire is the wave. This is the input from the power supply. Here is a sample wave with 1K, I believe. Let me see. 1K. Then we're gonna try 7K. That's 160 millivolts. About 0.2 right there. This is Thomas Youngston, ID 1131-79-59-1. Lab 4, exercise 4. The green LED is supposed to be the yellow one. The red is the red. Whenever I apply heat to my thermistor, they will turn on one after another.